start off this lesson with some practice of converting mixed radicals to entire radicals and vice versa. What we need to do is when we look at our root, in this case we have to check the index. The index is a square root, and we need to find then perfect square factors or multipliers. So we've got a perfect square multiplier of 25 times 5. That 25 can be taken out of the square root, so we can actually apply the square root here to the 25 and we get 5. And what's going to be left inside the square root then is going to be our root 5. So that 25 then inside is 5 squared, on the outside it's just 5. We do the opposite when we are going from mixed radical to entire radical. We need to then check the index. It's cubed, so anything on the outside must be cubed to bring it into the inside. So I'm going to end up with 3 cubed times 4. And notice that cube root of cube would just leave us with the 3 that we see on the outside there. And remember that this isn't that's an index there. That's not a power on that 3. So that 3 on the outside is 3 cubed on the inside. And we can actually work this out. The 3 cubed is 27. 27 times 4 gives us 108. Here again, check the index. It's square root. We can take out any perfect power factors, so any perfect squares. So there is a perfect square of 4. Now, since it's a bigger number, I'm not too sure if that's the only perfect square factor. So when I factor 4, 208 divided by 4 is 52. There is another perfect square factor of 4 here. So I'm going to rewrite this again. There's going to be 4 and another 4, and 52 divided by 4 gives us 13. Okay, so we have our two perfect square factors. They come out on the outside. If you like, you can just say that this is, if we have 2 of them, we can just take one out. I'll do them separately. Again, there's lots of different ways this can be done. This 4 here and 4 here end up as 2 and 2 on the outside. Okay, this is all multiplication, so we should put this together with multiplication. So we end up with 4 square root 13. So when we're doing square roots or any even roots, we have to be careful of some restrictions because we cannot do something like this. So if we try to square root negative 25, if we put it in our calculator, it says error. Okay, or something like domain error. And there's a domain error on this because there's a restriction on this square root. Because this technically is a square number. Okay, to get a square number, we need to have the same length and width on a square, or the same side length. There is no number, no real number anyways, that we can multiply x times x to give us negative 25. Okay, that doesn't exist. Because when we square a number to go from side length to area, if this number was negative, negative times negative would give us positive. Well, that gives us negative, and square answer is negative here. So that's not the negative. Negative times negative wouldn't work. If x was positive, it would be positive times positive, and that still would not give us a negative. So in order for us to square and get a negative, we need what we call an imaginary number. That's not a real number. Okay, so we need to kind of eliminate that. So we can explain this by saying that x squared must equal negative 25 by definition. The inside is our square area, and there's no number, and I'm going to just qualify this, there's no real number when squared equals a negative number. Okay, so this is not possible. So we cannot actually square root this. There's no real answer to this. Okay, so what about this? Okay, well, we did say that the square and square root are opposites. So would it be wrong to say that this is equal to negative 5? The square and square root undo each other, and we end up with what we started with. Well, given that reasoning that square and square root are opposite, this could work. And this is where it's a little bit difficult to understand, but the square and square root actually are not quite perfect opposites. Okay, the square root is something called the principal square root. Okay, the answer to the square root is always positive. So we're kind of restricted in that they don't quite undo each other, because when we square this, we get 25. Okay, negative times negative is positive, so we get positive 25. And when we square root this, we end up with positive 5, because the answer to the principal square root is always positive. So because of this fact that we start with negative 5, we square and square root, and we end up with positive 5. We don't end up with exactly what we started with. The square and square root are actually not quite perfect opposites. Okay, we kind of treat them as opposites most of the time. They are what we would consider inverses, in that they undo each other perfectly, and we end up with what we start with. Okay, but with the square root and square, there's a bit of a problem, because the square root is what we call the principal square root, and the answer is definitely 5. So this is the answer. So we should explain this by saying the answer to square root always gives us the positive version. Okay, and this is called, the formal name for this is actually called the principal square root. And it's because it's only going to give us the positive version of that answer. Okay, so in this case here, it doesn't quite follow our opposite rule, because square and square root, if that were really true, if they were perfect opposites, we would end up with negative 5, because the square and square root undo each other. And again, this is how we want to start looking at these operations. We want to look at these operations as functions and not calculations. If we look at this from the function perspective, we should expect it to do this, but it doesn't, because they are not perfect opposite functions or perfect inverses of each other. Now that last part there is a little bit of a difficult concept to digest, okay? But it's important to start kind of understanding things from that function perspective, and to start understanding why some things, where there's these kind of like loopholes in math, seemingly like loopholes, okay? And these things we'll further investigate and explain as we get into some other math.